All right, welcome back to ECE484, Fall 2021. Hope everyone is ready for tomorrow's exam or test. Before we start the lecture today, I just want to make a couple of comments about the test. So I posted the kind of instructions that you're going to see at the front on the first page of the exam. I posted that on Piazza as well as Learn. So take a look at that. The thing there is that, of course, MATLAB, so this was asked yesterday, MATLAB is permitted, or whatever, any sort of commuting program you want. But again, I emphasize that it's not necessarily going to help you, right? Like, the exam is not a MATLAB exam, and you can certainly get perfect without using MATLAB. There are 6 questions, just in terms of number of questions. The last question, the 6th one, is that kind of honor statement, right? So basically saying that you didn't cheat during the exam. So really there are 5 questions. And the 5th question is the true or false type question that you saw in the first term test, okay? So 6 questions, the last 2 are true or false, or true or false, essentially. And so there are 4 kind of regular types of questions, okay? All right, so that's all I'll say. And again, you'll receive an email at midnight tonight from Crowdmark, so please, think about when you want to start the exam, because once you click on the email and then you confirm, your web browser will open, and then when you confirm that you want to start the exam, you have a 3-hour window at that point. Okay, let's continue. So what did we do last class? We're finishing up our quick review of discrete time systems. Some of it is review, probably, some of it is not. And so the things we did last class was talk about how can you determine if a polynomial has all of its roots inside the unit disk without actually computing the roots, right? So of course, if I give you a polynomial, you can go to MATLAB and it'll give you a numerical answer of where the roots are of that polynomial. And that's fine if you have that. The value of the test that we talked about in that section is when the polynomial depends on a parameter. So for example, the sampling period that you're using in your digital controller, a parameter in the plant model, or a parameter in the controller, right? So this way it gives you constraints on those parameters, okay? We did not cover, so we covered the necessary conditions, but we did not cover the necessary and sufficient conditions. So you should read section 6.7 because that material, even though it wasn't covered in lectures, is something that I could ask about. Then we started talking about the frequency response of a discrete time system, and long story short, it looks very much like continuous time, okay? Like a lot of the things that when we talk about discrete time, there's an analogy to be made with continuous time. And so in particular, if you have a system, a linear time invariant system with transfer function g, which is rational and Bibo stable, we argued last class that when you apply a sinusoidal input, discrete time sinusoidal input to this system, in steady state, you get a discrete time sinusoid as output of the same frequency. So the frequency doesn't change, but there is a change in the magnitude and the phase. And those changes in magnitude and phase depend on the system, right? It depends on the model of your system, and in particular depends on what the system behavior is like. Okay. The one difference in discrete time versus continuous time is that instead of setting s equal to j omega when we do our frequency response, we are picking values of the discrete time of the z transform variable z on the unit circle, right? So instead of replacing points on the imaginary axis as in continuous time, we pick points on the circle, okay? And in the complex world, a point on the circle is just e to the j theta, okay? And theta determines of course, the angle. All right, and so if you were to plot the magnitude response, which would be this function versus theta, or if you were to plot the phase response, which would be this function versus theta, what you will get is essentially the complete information about how the system responds to sinusoidal inputs. Okay, so we're going to continue from there. Now, one thing you see from this picture here is that if, say, I wanted to plot the magnitude response of this discrete time system, what are we saying we have to do? Well, we're saying you pick z equal to a point on the circle, and then you vary theta from 0 to pi, right? And then that's your magnitude response. But what we see also, if we do that, if we keep going around the circle, obviously we get back to where we started. And so that means that the magnitude response, or really the frequency response, is periodic, right? It's eventually the information starts to repeat again. And it doesn't matter how many times you go around. It's periodic. Why is that? In continuous time, as we go up the imaginary axis, we don't get periodicity in the frequency response, but we're getting it in discrete time. So let's just make a comment about that. So the question is, why is the frequency response of a discrete time system periodic, but it isn't in continuous time? Why is it that you have this kind of difference? Well, in continuous time, for every frequency you pick of your sinusoid, so for every cos omega t is a distinct signal. And so what I mean by that is that if omega 1 is not equal to omega 2, then cos omega 1 of t is not equal to cos. Right? It's just different signals. If I plot them, they're not exactly the same at all time, values of t at all time. This isn't the case in discrete time. Right? So in discrete time, as I start changing that parameter, multiplying the time variable, theta, different values of theta produce the same signal. So we get that cos of theta k, of course, equals cos of theta plus 2 pi n k for all integers n. Okay? So what happens here is that these signals, even though the parameter looks different, this is some number, this is some number with a 2 pi offset to the power of n, they superficially look different, but it's the same signal. And so in particular, we get that the frequency response to cos theta k, the frequency response is periodic because the inputs cos of theta k and cos of theta plus 2 pi nk are the same. Okay, so if you're applying the same input, of course you're going to get the same response. And that's where the periodicity comes from. Okay? So that's why in continuous time, or discrete time, you go around the circle, you get this periodic frequency response. In continuous time, you do not. Okay, let's do one last example in this chapter. And what we're going to do is we're going to sample a continuous time signal and then run it through a discrete time system. So we're going to have the following picture. So there's our cos of a 100t, so 100 radian per second input. Sampling period will take t equal to 0.1 seconds. And our discrete time system will have transfer function 1/3 z squared plus z plus 1 over z squared. Okay, and we want to know what the steady state output of this system is going to be. Now, notice that the system is Bibo stable, right? It has 2 poles at z equal to 0, so that's inside the disk. So we can use the results that we saw last class to compute the response to this input. Okay? So first thing we need to do is we need to figure out what the input is to the discrete time system. So after sampling, what signal do we have? So in this case, the input to the discrete time system is cos of 100. And what do we do when we sample? We replace the continuous time variable t with k times the sampling period. So I'm going to write that as t times k. And in terms of our previous notation, notice this guy becomes theta. Right? That's our theta times k. And it has the right units of radians, right? 100 has radian per second units. I'm multiplying it by the sampling period with the seconds, so I get radians. Okay, and in this case, because the sampling period is 0.1, we just get cos of 10k. Okay, so we want to figure out the response to this input. Now, in this case, we could just plug in e to the j to the power of 10 into the transfer function, and we could get the magnitude and the phase of that complex number, and we'd be done. But what we're going to do is we're going to just comment that in the notes, in this example, you're given, graphically, you're given the magnitude response and the phase response of this system. But you're only given it for the range between negative pi and pi, or maybe 0 and pi. So you're not given it the value for theta equal to 10. You're given it only for theta between, again, 0 and pi, or negative pi and pi. And so what do you do in that case? Well, you just have to convert 10, this theta variable, into have to write it as some part between negative pi and pi plus some remainder. And so that's what I'm going to do here in order. So the reason I'm doing this is to be able to use the figure in order to get my frequency response. Okay. And this would be relevant if you didn't have the transfer function. In this case, because I have the transfer function, again, I could just plug in z equal to e to the j10, compute the magnitude and phase, and be done with it. But I'm going to suppose that we want to use the supplied graphical representation. Okay, so we continue. So I'm going to express theta in the form of some theta naught value plus an integer multiple of 2 pi. So in this case, we're going to say that theta sub 0 is in the baseband. So it's a number between negative pi and pi. Sometimes this is called the baseband. Okay? And n is an integer. Okay, you can always do this. And so in this case, we get that theta can be written as negative 2.56 plus 4 pi. Okay. And now that I have my baseband value, I can go and use the supplied figure, because the figure only tells me information from either, I believe it's from 0 to pi, but we can use the symmetry, the even and oddness of the magnitude and phase at that point. Okay, so that's the reason I did that. I wanted to get this component, the baseband component, to be able to use the figure. Okay, so now from the plots, in the notes, okay, what do we get? we get that the magnitude of g e to the j at the baseband, 256, equals, because this is an even function, that number, so it doesn't matter if I have a negative or positive on the magnitude side in the angle, and then from the figure I get approximately 0.22. Okay, eyeballing it off the figure. And we get that the angle of this complex number, use the oddness of the phase function, and then read it off the graph, 2.56, and I say that it's approximately negative 0.6. And so we're done. We've now got the magnitude change and the phase change, and we've now found the steady state output. So the steady state output is given by the same input frequency, change in magnitude, change in phase. Okay, you could keep the 10 here if you want, but it's the same signal as we saw before, right? If I have a 10 there or negative 2.56, it's the exact same signal. Okay, so that's it for chapter 6. What have we done in chapter 6? We've basically reviewed some discrete time system ideas. And the reason we're doing that, I've said it a bunch of times, is because we now want to design controllers in the discrete world, in the discrete time domain. And so that's why we did all that, so that when we start designing controllers, we have a good foundation as to what properties we might want from our controller. Okay, so we move on then to chapter 7. And this is sample data systems. Okay, so I remind you of our model of a computer-controlled system, right? It looks something like this. Okay, so I'll fill in this diagram and then I'll make some comments on it. Okay, so this is our standard feedback system with computer control. And this is our reference. Here's our tracking error, input to the plant, output of the plant. I haven't drawn a disturbance. You can add a disturbance if you'd like, but that's the basic setup, right? And the whole course really has been about how do I design that digital controller D, right? Because we want to implement the controller D on a computer to control this, in this case, physical continuous time plant P of S. Right? So something like the ball and beam in the lab, or a robot, or something of that nature. Okay? So what we want to do now is we want to convert this problem into a discrete time problem. And so what we're going to do is we're going to take this sampler and we're just going to move it around. Okay? And we're going to kind of just shuffle the blocks a bit. Okay, we're not going to change the diagram. We're not adding anything. We're not changing anything. We're just going to redraw this diagram in a different way. So what we're going to say is that the ideal sampler is a linear system. So when we talk about taking the sample of the tracking error, It's the same as taking the sample of the reference minus the sample of the output, which means I can move that S block easily past the negative feedback junction. So we can rearrange as the following diagram. Okay, let me redraw another diagram here. Could have taken it from the notes, but I think it's worth drawing. So this will be d of z again. This will be p of s. And then the hold still is here. And our sample will be here. Okay, so let me fill in the various blocks. So hold is here, sample is here, all right, sorry about that, it took a bit of time, but hopefully you agree that these two pictures are the same. Let me label some of these things. So this now we'll call R of K. This we'll call U of K. And this, of course, is Y of K. It's Y of KT. Okay, so hopefully you agree that these two pictures are the same. Okay, I haven't really changed anything. I just moved the sampler from sandwiching the controller to being at the output of the plant, essentially. All right. Now, we make a few observations. We've seen this sort of configuration before, right? Where we have a continuous time system sandwiched between a hold and a sample. And we call this the step invariant transform. And so let's kind of block that off. Right, so if I look at that block, this is what we're going to call our discrete system. So we're going to call this P sub d of z. And that's simply equal to what we called before, C to d of P. All right? And so if we look at that, if we can compute that quantity, that step invariant transform of P, and we will, then that puts us in a position to treat this sample data loop as a purely discrete time system. We now have a discrete plant, and we can use this discrete plant as the basis of control design for d of z. Okay, and that's what we'll do. So let me make a few comments here, and then I'll come back and say a bit more. So our objectives in this chapter are to learn how to compute PD, P sub d, study its properties, and compare the discretized plant to the original plant. Okay, that's kind of the high level of what we're going to do in this chapter. And then the big picture is that once we've done this, we're now in a position to treat our sample data system, right, mixture of continuous and discrete, as a purely discrete time system. So the nice thing about the way we're doing this is that we will obtain an exact discretization. Right? Unlike chapter 4, we will not make any approximations. Okay, we're going to get an exact discretization of our plane, and by that I mean that we're going to get exactly a model which models this block here exactly at the sample instances, regardless of the period, the sampling period. For any sampling period, it'll be exact. Okay, and like I said before, this will put us in a position to treat the sample data system like a discrete time system. And do direct design. Okay? So that's what we're going to do. Of course, we know that MATLAB can do this C to D computation, but we'd like to know what MATLAB is doing, first of all. Okay? And sort of understand why this discretization is the way we discretize plants. So I want to emphasize that when we discretize a plant, unlike a controller in Chapter 4, there is no choice. It's not a design choice anymore, right? Discretizing the controller was a design choice. You pick the type that works best, right? We went through a bunch of them. When it comes to doing direct design, we will always use the step invariant transformation. And it's because it allows us to make guarantees about the closed loop system in discrete time. Okay? Because there's no approximations. Okay, so that's the plan. And so we're going to first talk about how do you compute this step invariant transformation. And so we'll do it two ways. First, we'll do it in state space, and then we'll do it using transforms. Okay, so let me draw a picture here to give you an idea of what's happening. Okay, so the setup is as above. Where we're focusing on the plant part of it. And because we're doing state space, we're going to just treat the plant as having a continuous time state space model. Okay? And our objective is to get a discrete time state space model from U to Y. Right? And so what this will look like, for what we will get, is this block here. We want to write it as okay. So that block we're going to find a state space model for. Okay. As the notation suggests, the A and the B matrix are going to change, but the C and the D matrix will not. Okay. And so, again, drawing a big picture idea. We're going to go from a continuous time system to a discrete time system. And this calculation is what we're going to learn in this section. Okay? And then later on, we're going to do it the same sort of thing, but we're going to do it using transforms. So I'm going to draw a couple of arrows. So this, of course, is state space to transfer function, state space to transfer function. And later on, we'll see how we can go from G of S, P of S, let's call it P of S, to P sub d of z. Okay, that's going to be later on. But this is still going to be C to D. Okay, so this is the idea here. We want to get a discretization of a plant, and we're doing right now the state space world. So we're doing the top branch of this diagram. Okay, so if we just pause for a moment and think about this picture, what would be, how could we get a discrete time model for that system? Well, a reasonable idea would be the following. If I could somehow find the expression for the solution to this differential equation, right? If I knew x of t, not just its derivative, then I would know, what I'm sampling, right? If I had a closed form expression for the solution of that differential equation, I would know how to sample, or what the samples would look like based on the model. Okay? And so that's kind of the idea here. We're going to get a closed form expression for the solution of the differential equation. And from that solution, we're just going to kind of take that function of time, that's what the solution will be, and we're just going to pick out the sample instances from that solution. That's the basic idea. Okay? And so our first step in getting this discretization is to kind of understand the structure of the solution of the state equation, the x dot equation in continuous time. In other words, the solution of that equation, right? If we can solve that equation, then I can just sample it, right? I can just sample it in closed form, and I'll know what the resulting discrete time model is. Okay? And again, I don't want to just do it numerically. I want a model. I want a discrete time model so that I can do control design. Okay? So with that in mind, we're going to talk about the solution to the state equation. And I'm only going to talk about a high level, give you the high level idea. There's more details in the notes, but we'll see how to do it. Okay, so we seek an exact solution of, right? Because we want it to be exact, okay, exact solution of the following. Okay, the reason we want it to be exact is because if we just were going to do approximation anyway, then, well, just do emulation, what we've already done. Right? Then we're back in the same boat we were before, which is, okay, if the sampling period is small, the approximation is good, and things should work well. We want something that should be able to handle large sampling periods. Okay, so that's why we want this exact expression. And so we need a little bit of machinery to be able to do that. And so to be able to do this, we need the matrix exponential. Okay, so I'm going to define a matrix exponential, and the reason I need it is because it shows up in the solution. This matrix exponential shows up in the solution of that differential equation. Okay, and so let's first define it. Okay, we're going to say that the matrix exponential of A being a real n by n matrix is the following. Okay, and I'm just going to copy, or formally copy, the scalar definition of an exponential, right? So I'm going to write this as I plus a plus 1 over 2 factorial a squared, etc., etc. So it's going to be the usual exponential, right? So if a was a scalar, this would be your familiar exponential, but it's a matrix now. Okay. So there's some properties of this matrix exponential in the notes. I guess I'll say the following. This series converges for every matrix. So it doesn't matter what A is, it's always well defined, this matrix exponential. And it has properties that are very much, similar to what you expect from the scalar exponential. There's a few differences, a couple of key ones, but for the most part, it's very similar. Okay, and we're going to use it in our solution. Okay, again, I'm not going to go over the derivation in class. You can look at it in the notes if you're interested. But it turns out that if I use this matrix exponential, I can get an exact form of the solution of that differential equation. So using the matrix exponential, we can show, see the notes, that x of t, the solution of that differential equation, can be written in the following way. The matrix exponential with a t multiplying the A matrix times the initial condition plus the forced response. Now, and this is continuous time, so we're going to get integrals instead of sums, okay? But same sort of idea. Okay, that's a convolution integral instead of a convolution sum, but that's the same idea. Okay, so let me make a few comments. This guy here would be our natural response. This is our forced response. And that whole thing together is the total response, the response of that for t greater than or equal to 0. Okay, and okay, so the reason again why we want this expression is because I want to sample it. I want to be able to sample it and pull out the discretized A matrix and the discretized B matrix. All right. Now, we want to be able to, at least for small problems, compute some of these things by hand, get an idea of what MATLAB is doing. And so to initiate that or to facilitate that, let's compare this time domain expression. So remember, the time domain expression we just derived is the solution of this differential equation. But we know from previous courses that a nice way to solve differential equations is to use Laplace transforms. We just saw it with discrete time systems. We use Z transforms. So let's do the same thing. Let's take the Laplace transform of this guy and then compare the two, the time domain solution to the Laplace domain solution. Okay. So in terms of Laplace transforms, right, if I were to take the the Laplace transform of that differential equation, we've seen this before. The only difference now is that I'm not setting the initial condition to 0. I want that natural response to show up. Right, so this is the same sort of thing that we did when we were going from state space models to transfer functions, but there, because we were looking at a transfer function, we assumed that the initial conditions were 0. Here, I've kept the initial condition, the x sub 0. Okay, rearrange. And we get the following. Okay, so we have x of t in the time domain, x of s in the Laplace domain. So if you compare those two expressions, just like we did in the discrete time case, you see that this matrix exponential is a Laplace transform pair with this guy. because that's where the initial condition shows up in both of these expressions. So comparing x of t to x of s, we conclude that the Laplace transform of e to the ta is equal to si minus a inverse. Okay, and so this is very evocative of our discussion that we had in discrete time, right? Where in discrete time, we talked about the Z transform of the transition matrix being a certain quantity, and here we're finding that the Laplace transform of the matrix exponential is another quantity, and actually quite a similar quantity, in fact. Okay, and so indeed, e to the ta is to continuous time as a to the k is to discrete time. Okay, so let's just do an example of computing a matrix exponential to say that it's not too, it's very similar to what we've already seen. So example 721. I want to solve a certain differential equation. For some initial condition where a, in this example, is given by 0, 1, -2, -3. All right. So I want to solve this differential equation. We have this general equation. Oops. Above, we derived the general solution. Let me just scroll up for a second. There's x of t with the natural response and the forced response. In this case, there is no input, so I'm just going to ignore this part. And so the solution is just that guy there, right? Because u is equal to 0. So I'm just looking essentially for the natural response. And so I need to compute this thing if I want to solve the differential equation. All right. Now, we could do it algebraically, just like we were when we were solving for a to the k, but we could also use this observation from above. This one, and that's what I'll do in this example. Okay. Okay. So we have I have to compute this thing and then take its inverse Laplace transform. That's how I'm going to get e to the ta. So this guy is that. And I claim that if you do the calculation, you get the following. Okay. And so just like when we were doing our discrete time state transition matrix, I'm going to have to take the inverse LT of each entry in this matrix. To get. Okay, so that's a time-consuming step, obviously. Right? You're going to do partial fraction expansion 4 times, once for each entry in that matrix. There's nothing too interesting there, but I'll just write down what we get. Let me just make sure I don't make any mistakes in writing this down. Okay, And that's our solution. So the solution is given by that expression. And you can plug in different initial conditions and so on. But you see here, of course, you look, it's not really central to our discussion, but you have something analogous to what we would have called asymptotic stability in discrete time. Notice? It doesn't matter what initial condition you pick, this matrix here is going to 0. Okay? And so in continuous time, you'd also call that asymptotic stability. But that's not central to our discussion. Okay. So I'll just mention in passing that e to the ta can be computed using diagonalization, or more generally, the Jordan form, just like a to the k. Okay, I won't go over that, but basically everything you can just say about a to the k, there's an analogous thing for e to the at. E to the at, yeah, e to the at. Okay, so now that we have this solution in hand, right, we have this guy. We also talked about how to compute the kind of the weird part of this expression, this matrix exponential, maybe the unknown part. We're now in a position to compute our discretization. So let's do it. Okay, let's now compute c to d. All right, and so the picture, I'm going to just copy it from above. It's the same picture. Just want to remind you what we're doing here. So what we want to do in this derivation to get the c to d, I'm going to use my general solution that we had above, and I'm going to use it to model the evolution of the continuous time system over one sample period, right? So I'm going to take my initial time, instead of being t equal to 0 as we did above, I'll take my initial time to be sample period k, sample instance k, and then I'll see what the solution does over one sample period. Okay? And so in knowing what the solution will do over this one sample period, I can generate a discrete time model. So that's the idea. So let's bring in some notation. I'm going to write, because otherwise things are going to get hairy notation-wise. I'm going to write t sub k for kt, right? So t sub k is the time corresponding to the kth sample instance. Okay. And then I'm going to make the comment that if we know the state at time tk, or so at sample instant k, and you know the input over a sample period, so we'll write that as tk less than or equal to t less than tk plus t, and point out that this is just tk plus 1. So if I know that, if I know the state at time tk, so the kth instant, and I know the input that I'm applying over that range, I can use my solution from above. And so we will get so the time that's advanced is just that. So there's the natural response over this time instant, or this time interval, I should say, plus we have the forced part of the response, depending on the control input. So I will write that. Okay. All right. So I'm going to stop there. Ran out of time. But basically, we've now got this solution over a sample period, and then we will use it to get our discrete time system. Okay, I'll stop there. If there are any questions, I'll answer them. Otherwise, good luck tomorrow, and I will see you next week.